and it is recording. Okay, so we're good on that. And I guess what we want to do then is to dive in to our discussion. Our discussion now is currently, we're still talking about charge and matter, but we're now looking a little bit about how charge flows in matter and the important aspects of electricity in conducting matter, and how we're going to tie this all together with energy and the energetics of stored in an electrical circuit and how we harvest the energy out of that circuit. But preliminarily here, what we're doing is just talking a little bit about the nature of how we have developed this energy source. It's a stored form of energy in the form of electrical potential energy. Now, potential energy is a form of energy that we harvest. There are many types of potential energy out there, but certainly at this juncture, there's two absolutely top-notch, most critical potentials, sources of energy we harvest. One is fossil fuels, and the second is electricity. Now, typically we make the electricity from fossil fuels anyways, so probably it all begins with fossil fuels. Fossil fuels are stored energy, and we harvest that energy to make motion or make heat. And it turns out motion and heat are the same thing, as we will learn later, but we harvest from fossil fuels this energy to move things around and to keep things warm. And the other source that we prefer when we're not burning fires or we're internal combustion engines is to harvest energy from an electrical source. And meaning we plug things into the wall, we make lights come on, we plug things into the wall, we warm the room, we plug things into the wall and actually lift elevators up and down in buildings. So again, this idea of the energy stored in electrical circuits can be converted into forms of energy we use. Now, one reason we really love electrical energy is that we've, over the past 150 years or so, developed an infrastructure that allows us to pipe this energy very efficiently from section to section or from region to region, so that we can have, everybody doesn't have to have an electrical generator like we have to have a internal combustion engine to harvest fossil fuel energy. We all have to, you have to basically burn the fossil fuel in some kind of engine and have that engine convert it, the fossil fuel energy into motion for you. What we have learned with electricity is we can just pipe this electricity from a central source, and it provides a well of energy, if you like, that we can convert into these other forms, and then we use these other forms. Okay, so again, right at this juncture, what we're preliminarily doing here is just learning a little bit about the nature of the electrical storage system. And it goes back to what we have been talking about previously, which is, of course, charge. And so in the course of today, I hope we're going to develop the two main ways in which humans have learned that we can use this electrical process, or the difference between plus and minus charges, in order to store energy so that we can use that energy at later times for whatever whim we might happen to have and whatever desire we have to use that energy for. Okay, so what I'm next going to do is start with my slides, as we usually do as well. And what did I hit? All right, I can't even see what I'm doing here. This is just so terrible. I'm going to present like I always do, and I'm going to click on the thing like I always do, and get everything going here. So apparently I am now presenting, and what I wish to present are my slides, and I believe this is where we left off in our last meeting on Monday. So this is where I'm planning on starting this time. We made a definition, first of all, of what we're going to call an electrical current. An electrical current, just like a water current, is a flow. But instead of having moving molecules of H2O in an electrical current, we're going to have moving electrons. And to facilitate the motion of electrons, you have to have a conductor. A conductor is a viaduct or a methodology by which we can transfer electrons and move them around without much loss of energy. Essentially, any material will conduct, but it's just a fact that when certain materials are forced to conduct, you have to pay a price. And that price will be part of the energy that you could have harvested in that electrical well of energy. So we prefer to use certain materials that are really facile towards the movement of charge through them. So then we're not wasting energy pushing charge through them. We can harvest all the energy we want and convert it into various useful forms. So the first thing that we're going to do then with that regard is to define this quantity by which we're going to be measuring this or harvesting this energy in terms of the charge. And as we did at the end of the period last time, we defined a value I, which is universally used in the physics community to represent current. And current is flow of charge here, not flow of water, as I said. So what I'm going to define it with this Greek symbol delta on the top and bottom is, as I talked about last time, it's change. Delta in science always means change. If you have delta V, you mean VF minus VI for the change in volume. If you have delta T, you mean TF minus TI for the change in temperature that a system undergoes. Here, that is delta capital T. When we have delta little t, as you see in the denominator of this expression, that means change in time. Typically, when we start a clock, we call that time 0, and then we stop the clock at some final time, and really you're looking at the elapsed time or the change in time from the start of a process to the finish of a process. So that's what the delta t means on the bottom. And the delta Q on the top is the flow of charge, how much charge has passed by some reference point over the period of time that you're measuring the motion of the charge. So if you remember from our discussions on electrostatics, Q is the universal physics symbol for charge. So I'm looking at change in charge, if you like, or flow in charge past a given point over some period of time that I'm going to measure that charge. Okay, so these little red boxes are just saying those things that I already said, so I'm not going to say anything else about them. The units of current are the units of charge divided by the units of time in the SI world, and that would be coulombs per second, but because of our deference to a famous French scientist who pioneered studies of charge and motion, we named this unit after this individual, and his name was Ampere, and more familiarly, we shorten that and call it the amps of current. So the amps of current will measure how much charge flows per second, and 1 amp would be 1 coulomb per second. And I believe I talked with you about the fact that 1 amp of charge flow is quite significant when you consider that each electron only carries a charge of 1.6 times 10 to the minus 19 coulombs. So if you want to get 1 amp or 1 coulomb per second passing you each second, you're going to have on the order of 10 to the 18 electrons flying by you per second. And that's a huge number of electrons. And again, I think I pointed out to you that typically in house circuits, 1 amp, 2 amp, 3 amp things are used, but devices such as stoves and dryers and air conditioners, they certainly would use 10 amp, 15 amp, 20 amp currents. And they have to pull a lot of juice, if you like. The more energy the device consumes, the more current you're going to have to supply to that device in order to get the energetic requirements that it wants. So you're going to have it feed it a lot more flow of charge per unit time, that's for sure. Okay, now if you have a direct current, and this of course familiarly is given an abbreviation DC. If you have a DC current, the charge flows in one direction and one direction only. And that seems obvious that that should be essentially the only kind of current that we would generate. We're going to flow charge from point A to point B, and it seems like every electron would prefer to move in the same direction when we're flowing our charge from point A to point B. Well, it turns out that that is very commonly employed, yes, but it turns out that that's not the easiest or most economical way to develop current, as we will see. The more economical way to make it and to make it as cheap as we can and as much as we can for our everyday uses that we have developed over the past 100 years for electricity, turns out that we do so by using what is known as alternating current. And alternating current has the abbreviation familiarly, even to your mom and them, of AC. So there's a difference between an AC circuit, which carries charge, and a DC circuit, which carries charge, which we will be illuminating during our time here. Okay, so let me first talk about some uses of current and their connections with magnetism. The first one I want to discuss is the amplification of sound or the recording of sound. So both of these pretty much take the same, employ the same tricks, whether we want to amplify the sound or whether we want to record it and store it for some future use. First of all, you have to capture the sound. And whether or not you want to capture a vocal performance, whether you want to capture instrument performance, or whether you just want to capture the sounds of nature, the buzzing of the bees and the chirping of the birds, or whatever you want to do. Pretty much we use the same kinds of technology in order to accomplish these things. So what we're going to do is convert sound, which is a wave, into a signal that is electrical or charge in motion, so that it can be recorded or amplified from this device. Now, when were these sorts of things developed? Well, I would say beginning around the 1850s, when Marconi was looking at transmitting radio waves, and through the time of Edison, which is into the late 1800s, early 1900s, mid 1800s to early 1900s, when the wizardry of Bell Laboratories and the things that Edison was able to pull off. This was the seminal years when we were learning how to do all these really clever things with electricity as a method of storing information and even enhancing information by amplifying it after you record it. Okay, so the two most common types of microphones are either a dynamic or a condenser one, and I might say a word or two about either one here, but generally we will talk about the dynamic microphone because that's the one that's easiest to understand with what we know about magnets and what we talked about last time about the phenomenon of Lenz's law. Now, let me briefly remind you about one of the weird things that was discovered by the German physicist Lenz and the English physicist Faraday. The weird thing that they discovered was that if you take a conducting material and you place this conducting material in a magnetic field, it gets conditioned to like the magnetic field. Meaning, remember what I talked about with one of the things conductors do? They have mobile charge. So in the magnetic field, their charge becomes mobile and it becomes aligned in this magnetic field in a way that, for lack of a better way of describing it, I will say, makes the conducting material comfortable. So the conducting material is comfortable in the magnetic field that it's being bathed in. Now, if you attempt to change the magnetic field in a conductor, it suddenly says, wait a minute, I don't like this change you're doing to me. And in a way, I'm trying to make this inanimate object, this metal or material, into a thinking entity. And of course it isn't, but this is kind of the way I think makes the most sense to think about what's going on here. Even though this conductor has no animate ability to reason what's going on, it seems as if the conducting material knows you're changing the magnetic field that is being subjected to. And what it says is, I don't like that. I'm going to make a change in me to oppose what you're doing. So if you try to lower the magnetic field that a conductor is being bathed in, it generates its own magnetic field to replace the magnetic field you're removing. This is just such a bizarre concept, but that's exactly what the conducting material does. How does it generate a magnetic field to replace the magnetic field you're removing? It moves charge. So charge naturally begins to flow in the conductor because moving charge makes a magnet. So to replace the magnetic field that the conductor is feeling that you're taking away from it, it starts to move charge around in it to compensate for the loss of magnetic field it's being subjected to. What does that mean? You have created a current in the conductor. Now this works in either direction. It works if you increase the magnetic field that a conductor is subjected to, or it works if you decrease the magnetic field that a conductor is subjected to. What it ultimately does, though, is whether you're increasing or decreasing determines which direction the conductor itself will generate its internal current in order to build a replacement magnetic field. So just for instance, we'll say if you build and enhance the magnetic field you subject the conductor to, it makes a current to the left to kind of work against what you're enhancing it with. If you lower the magnetic field, it makes a current to the right to try to replace what you're removing from it. So in that sense, now we can envision that I'm going to get an alternating current in the conductor depending on whether or not I subject the conductor to an enhanced magnetic field or a diminished magnetic field. So that's just such a bizarre property. It's, again, it almost gives this material, this inanimate material, this conductor, some kind of reasoning and logic that says I will do this process in order to replace what is physically being done to me. And of course, there's nothing like that involved in what's going on, but that's what it seems like. So what I'm getting at then with regard to making a device such as a microphone is that we use these kind of tricks now in order to take the sound and convert it into an electrical signal. When you make that simple understanding of moving of magnets moving around and how they can generate charge, or charges, or if a conductor wants to make a magnet, it has to move charge, then we can now maybe envision how a microphone can be designed or devised. So a dynamic microphone operates using this idea of magnetic induction. And that's the one that we're going to focus on because that's what we spent our time talking about yesterday, or I mean on Monday. And what we have is we generate a changing magnetic field within a conducting loop. And that changing magnetic field within a conducting loop will make a current in the conducting loop. Now, what makes the changing magnetic field is that there are magnets internal to the microphone itself. And I think I have a picture of this, but I guess it's on the next slide. So what we're going to do, and there's a bunch of words here. I'd rather show it to you in a picture, but we're going to use the idea of Lenz's law to see if we can convert a sound wave into a signal that we could transmit or record. So this is kind of an ugly cartoon that I drew. So it's not your best cartoon of what a microphone looks like, but this is attempting to make a simplified picture of it. And let me try to explain what my picture is showing. The vertical thicker line is in the microphone what I would call a diaphragm. Typically, the diaphragm is a piece of cardboard. And the piece of cardboard is inside, usually it's to keep it from being damaged, it's inside a wire mesh. We've all seen a microphone. We all know what we look like. So when you hold a microphone up to your face, you're of course speaking into this wire mesh. And again, the wire mesh really has little to do with the action of the microphone other than to protect this delicate cardboard diaphragm. So the idea is this: when you talk, you generate sound waves, of course. But what are sound waves? They're what we would call pressure waves, meaning I push bunches of air. My mouth literally bunches up air molecules and spreads them, bunches them and spreads them, bunches them and spreads them. So I send a pressure wave through the air. This cardboard diaphragm inside the wire mesh now is flexible enough so that when the pressure wave hits it, it dances. And it dances in and out with the pressure wave. Now, a few things that you can imagine with the pitch of my sound. And of course, that's the tone I'm making. That is proportional to the frequency of the wave. And I think that kind of makes sense. High-pitched sounds are high-frequency sounds. Low-pitched sounds are low-frequency sounds. So what that means is the rate at which the diaphragm will dance is going to tell you something about the frequency of the wave. If I give it a high pitch, then the diaphragm wiggles back and forth with a very high frequency. If I give it a low pitch, then the diaphragm wiggles back and forth at lower frequency. Okay, so that's item number one. The frequency of the tone that I make will tell you something about the rate of oscillation of the microphone. It'll oscillate rapidly for high-pitched notes. It'll oscillate slowly for low-pitched notes. Now, the second really interesting thing is the amplitude of the wave, meaning there's certainly a matter of how fast it's moving back and forth, but there's also a matter of how far in and how far out it swings. Now, just like you can envision for your little sister on a swing on the playground, the further the amplitude or the further the back and forth, the more energy that is present in the wave. And what that is proportional to is the energy of the wave is proportional to the loudness of the wave. So when I speak softly, the wiggle of the diaphragm will only be slightly significant from the starting point. The louder I get, the further and further the diaphragm will swing. So there's these two factors. The distance that the diaphragm moves will capture how loud your signal is that you're sending through the microphone. The speed or frequency of oscillation of it will pick up the pitch of your sound when you're making the sound. Okay, so that's how the diaphragm works. Now, attached to that diaphragm, you see a bunch of circular wires, and those are connected conducting, that's a connected conductor. So there's a loop of conductors that are going to be connected to the diaphragm. Then in the center of the loops is a magnet. Every microphone of this type has a magnet in there as well. And as the diaphragm dances, it moves the coils. The sound waves hit the diaphragm. The diaphragm dances. As the diaphragm dances, it pushes it onto the magnet and off of the magnet. And as it gets pushed onto the magnet, it changes the magnetic field that the conducting loop experiences. As the magnetic field changes for the conducting loops, they say, I don't like that. Remember what I talked about before. The conductor doesn't like a change in its local magnetic field. As soon as it starts dancing, the field is constantly changing. So what is the conductor doing? It's constantly generating its own current by itself with no attached power supply, with no anything else. It's making its own current, and that current is varying and attempting to either replace the magnetic field that it's losing as it dances around the magnet, or enhance a magnetic field that it's experiencing as it dances around that magnet. So there's an electrical signal generated that can be captured from the dancing coil, and then you can transmit that. We can do various tricks. We can record it. As a matter of fact, most of our early recording devices were magnetic themselves. You sent this onto a magnetic tape, and what it would do is line up little particles. The current that passed by the tape would line up particles on the tape and literally record this oscillating signal by changing it into magnetic information. After, it's kind of interesting. We start out as physical sound information, transmitted into magnetic information, transmitted into electrical information, and then the electrical information, if you're going to store it on tape, goes back to magnetic information. Then, of course, we'd have to harvest the magnetic information off the tape in order to send it back into electrical form. And then we send that electrical form to a speaker, send it to a magnetic form, and bounce it back out again. So all this is due to our tricks with the interplay between magnetism and electricity. Okay, so I'm just going to leave. Look, we didn't talk enough about this type of interaction in an electric field, but we did talk about the magnetic one. So this idea about the condensing microphone, I'm leaving it out. I might ask you a question or two in the near future about the dynamic microphone, but I don't think I'm going to ask you, and it's not that I don't think, I know I'm not going to ask you anything about the condensing microphone, since we didn't spend any time at all talking about the idea of storing electrical information, not magnetic information. So I'm going to leave that one out. Okay, so let's just now pretend that we have a rudimentary understanding of how a microphone works. It's really just got a magnet in it and a coil of conductor, and it's got a diaphragm that dances as you spit words into it, and it changes a magnetic field that a conductor experiences, which makes the conductor make electricity. So you're recording that electrical signal. And the bigger the peak of the electrical signal means the louder the sound that was going into the microphone. The frequency of how quickly it's oscillating between peaks and troughs is something to do with the tone. The quicker the oscillations, the higher the pitch of the sound. The slower the oscillations from peak to trough, the more bass type the sound is. Okay, so I'm sending this now into a tube of electrical conductor away from the microphone. Now what am I going to do with it? Well, I could store it, as I said, but another thing I might like to do with it is amplify it. Send it out to a football field so everybody can hear me. Send it out to a rock concert so everybody in attendance, even in the back row, can hear what I'm doing. So let's look at what we do on the other end with this electrical signal to do that. I'm going to tell you very simply, you just do the opposite. Literally, at the other end, to amplify this signal, I'm just going to do the exact opposite that I did at the receiving end of the sound wave. Now I'm going to generate a sound wave in exactly the same way. So just like microphones, loudspeakers can either be made with electrical tricks or using magnetic tricks. And again, since we're focusing on the magnetic tricks, we're only going to look at how to do it with an electromagnetic speaker. Now, first thing I want to point out to you is you have probably noticed that whenever you have decent speakers, they have some girth to them. They're quite heavy. And if you have ever opened up a speaker, you will notice a big, solid metal chunk in there that is a permanent magnet. You get your keys out and stick it on there, and they will stick onto the speaker. Because what we're going to do in order to generate and regenerate the sound that we've now changed into electricity is we're going to literally do the opposite, which requires us to use a magnet to pull that off. Okay, so it operates like the dynamic microphone in reverse. And let's just skip the electric one because, again, I should have taken those words out. I really did intend to, and I thought I did. Apparently I didn't. So we're just going to focus on the one that uses the magnetic trick. And literally, this is what it's ultimately going to look like. Now I will have a signal coming down a tube. And I don't want to try to move the magnet. That's pretty heavy. But I will have this coil that carries the signal from the microphone that is an oscillating electrical impulse, depending on whether the microphone was dancing in or dancing out, enhancing its magnetic field, reducing a magnetic field. It will make this varied pitch, varied frequency signal of various amplitudes, depending on loudness, and I will send it down the coil, and I will have a permanent magnet that is stationary. But now what will happen is as the charge moves through that coil, it will be generating different magnetic interactions with the permanent magnet, so it can make the coil dance. So now the coil will be dancing on this end of the system, and what I have is at the edge of the coil, I have it attached, as you can see, to this vertical thick black thing, which again is another diaphragm. And I'm sure if we've all opened speakers, we know that there's some kind of cardboard center to them. And what that cardboard center now is going to be pushed in and out by the coil of conducting loop as it dances over top of this magnet as it reacts because of the different frequency and amplitude of the electrical signal going through it. It's going to react by pushing or pulling on that coil to either lesser or greater extent, which is going to push or pull on the air to a given extent that will generate a sound wave of the right pitch, of the right frequency, of the right loudness or varying loudness that can be sent out. And because of what we would call acoustical engineering, where I design the cone around the diaphragm properly. And and another thing that's commonly done is that there's an amplifier in there. We've all heard that you have to attach an amp to the signal. So when you send it into the microphone, what I'm getting at is that the amplitude of the electrical signal from the dancing magnet on the microphone, pretty pathetic. I think if we held a microphone in our left hand and a speaker in our right hand, what we would quickly learn is, wow, the speaker is way heavier than the microphone. So there's only a very small magnet in the microphone. There's a huge magnet in the speaker. So there's only going to be a very low current signal that you're going to capture with the microphone. But if you send that through an amp, the amp literally enhances the signal. It doesn't change the frequency of it or things like that, but it changes the above and below the 0 point of the oscillating current. It changes that dramatically, which now when you send it to this much bigger magnet in the speaker, makes a much enhanced sound pumped out of the speaker. So there's invariably going to be some amplification of the signal from the microphone to the speaker in order to get the desired effect of amplification of the sound, for sure. Okay, so I guess the bottom line is what all we're going to do is in the microphone, we're going to let the diaphragm be hit by the wave, and it's going to cause the coil to dance, and causing the coil to dance puts it into an electrical signal. And then on the other end, we're going to send the electrical signal over a magnet, and that's going to cause the coil to dance, and the coil pushes on a diaphragm and sends out an amplified signal that can be, as I said, broadcast into a football stadium or into a concert hall. Okay. Oh, now maybe one more thing I would say, because this is also an interesting story. And it's not so relevant as it was when I was a kid, but it is kind of cool. How did a record player work? And how did Edison invent a record player? Well, we've all seen a record. There are these chunks of plastic. They have little grooves in them, and you put a needle in the groove, and then there's recorded music on the needle. Well, really what is in the groove, if you could get down in there and look, is that there's various heights of plastic melted in each groove. Some regions of very high height, some regions of very low height depth, if you like. And the frequency at which the hills of plastic vary there's going to be varying regions of like really rough regions and really just gently rolling regions. So here's what's happening when you spin this record. The record spins, you put the so-called needle down into the groove, and the needle is kind of like on a little piston. The needle can ride up and down over the peaks and valleys that are in the little plastic grooves. And what that does is it moves the needle up and down over the grooves. And guess what's in the needle? A little magnet, the same kind of setup that was in the microphone. So I'm going to ride the grooves, and it's going to ride up and down and move a conducting coil in the needle over a magnet, and that's going to generate an electric signal that can be piped away from the arm of the record player and sent to a speaker. And then the speaker can transform it back and spit the sound at you. So the groove of the needle is the key. Somehow they learned how to take a device that could imprint, varying with the sound, the depth and peaks of each groove, the frequency of each groove, the amplitude of the groove, so that it tells it how loud to be, the frequency or how quickly the bumps change from plus to minus gives you the tone of the sound. And of course, over 100 years, this was developed into quite an important way to transmit or record sound and store sound and share sound. Well, of course, I'm pretty sure we're all familiar now. That's all out the window. What we call things like that nowadays, we call that analog sound, because it's kind of mechanical in the sense that you have moving parts that are generating the electrical signal. What we have learned to do over the past 50 years is digitally record the sound with ones and zeros as being plus or minus, being up and down. So now we digitally record it. So we use like MP3s and stuff like that. We don't use cassette tapes. We don't use records. We don't use 8-tracks. We don't even use DVDs or CDs. CDs were kind of the same, but they did it with light. But now we just simply have it stored digitally in a bunch of ones and zeros, and the ones and zeros are read to give a sound wave. Okay, so unfortunately, a lot of the wizardry that went into acoustics is long gone. Boy, I'll tell you, when I was a kid, the record store and where they sold the speakers and the turntables and all that, if you had these fancy things, you could pay thousands of dollars for a high fidelity speaker system with turntable and amplifier. Wow, a lot of my crazy friends back in the 60s spent a lot of their money on these sorts of things that are completely obsolete now. A lot of people claim the high fidelity of the music is better. I don't have a discerning enough ear for it to sound any better to me. So it's much cheaper to do it digitally, much more transportable. Records suffered the problem of getting scratched or just getting otherwise just problems with the storage system that you use for the records. Once you put it in a digital form, it's pretty much universal, and you can transfer it over the phone to somebody else if you want. You can. It's just got so many more benefits that the old way of doing business is completely out the window. Okay, so let's now move on to, again, I guess I'm kind of hopping around to a certain extent, and I do apologize for that. But now let's return to the idea of the DC circuit and how this has come about, how the evolution of passing electricity through wires to your home, or using electricity to generate energy or to generate the kind of things that make our lives so much easier and facilitate the things that we like to do because of this energy storing system. So let's first return to like the chemistry of what goes on at the atomic level when we're going to let charge flow. So this is what chemistry says at the basic level would happen. Let's suppose I take a beaker. It is actually a pretty blue beaker solution like this of a material known as copper sulfate. And at the bottom there, under my little recording button, you see it says CuSO4. That is known as copper, Roman numeral 2, sulfate, to pay tribute to the materials that go together to make this entity. Now, the beaker is not only full of copper sulfate, though. What it actually is copper sulfate solution. And invariably, if you have a solution, of course, it's liquid. It doesn't have to be. So we should mention that before we go any further. Solution almost invariably means a liquid base, but that's just the more typical form in which we deal with solutions. When a chemist says solution, what a chemist means is a homogeneous mixture. And a homogeneous mixture means if I have a solution and I can look at it nanoscopically, so I can see everything that's really in the solution, and I scoop near the upper right-hand corner and count the ratio of the components, and I scoop near the bottom left-hand corner and count the ratio of components, and scoop near the middle and count the ratio of components. In a true solution, the ratio of components is the same throughout. Okay, so if I have a liquid solution, typically it means this material is mixed with water. Okay, now that doesn't necessarily always have to be the case, but since water is so ubiquitous to our planet, we almost invariably believe if you have a liquid solution, that water is part of that liquid solution. And that's a pretty good guess, because I would say 99.99% of the time that I'm dealing with a liquid solution, then water is the major component of that liquid solution. We essentially are a liquid solution of a little bit of carbon and a little bit of phosphorus and some calcium and other things like that, but mostly water. There's no doubt about that. Actually, we're not a solution because we're not homogeneous in the sense that I'm talking about. But, okay, a solution is homogeneous in the sense that it's got the same proportion of components no matter where you look at it. Now, as I mentioned, we're most familiar with liquid solutions, but there can be gas solutions. And the most familiar of those, of course, would be the stuff we breathe. Air is a solution of gases. It's a homogeneous mixture of mostly nitrogen and a good bit of oxygen. It's actually 78% nitrogen, 20% oxygen, 2% everything else. Now, what that means, if you have 100 molecules of air, 78 of them are nitrogen, 20 of them are oxygen, 2 of them are something else. What might the something else be? Carbon dioxide, water vapor, various other things like radon gas, various pollutants that we have dumped in our atmosphere over time. But that would be the homogeneous mixture. I sample the air here, sample the air here, sample the air over here, and I would find this ratio of mixtures no matter where I look. Now, you can even have solid solutions, believe it or not. Things dissolved in a solid homogeneously. Familiar to you would be something like what we call brass, which is copper mixed with tin. Depending on how much copper you mix with the tin, you get various forms of what we know as brass. And typically to make them, you liquefy the copper, you liquefy the tin, you stir them together, and they mix homogeneously, and then you let it solidify. Now you have a solid solution, if you like. So we can make solutions literally of any phase. Again, I would mention liquid solutions, far and away our most popular type. Now, to contrast the solution, just let me point out things that aren't solutions. We call them suspensions. And what can I offer to you as a suspension? Well, a most common one would be fog. Fog is what we often call an aerosol, or it's a form of aerosol where you have liquid droplets dispersed in gas. So when you see fog, you're seeing condensed water that isn't thick enough to form a liquid puddle yet, but it is liquefied, meaning there are several, it's not individual water molecules because you couldn't see them if they were individual. There are large numbers of water molecules still suspended in the air. Now, what I'm getting at is it's not homogeneous, meaning there's regions where there's a little bit thicker fog and a little bit thinner fog. There's not going to be a homogeneous dispersal of this liquefied water suspended in the air in a typical fog. Another thing would be smoke. Smoke is a suspension. Now it's solid, suspended in gas. The little tiny particles aren't technically liquid. The little tiny particles are technically solid in something like smoke. Mostly carbon ash particles floating around in the smoke. And of course, I think we can envision there'd be regions of thicker smoke and regions of thinner smoke. It doesn't have to be homogeneous throughout a smoky region. All right, so that's the basic idea of what I'm saying is a solution then. In my solution, if I could look nanoscopically, I would definitely find the copper sulfate that's present. The majority of what's actually in there, though, is water. So water is kind of like the theater or the arena in which I have placed this copper sulfate. Okay, now what I'm going to do is I'm going to stick a silver piece of zinc down into the copper sulfate solution. And I'm just going to let it sit there. And then after a little brief period of time, maybe 20 minutes, maybe 30 minutes or so, I'm going to pull the strip out and it's going to be changed. It's not going to look the same anymore. And I'm indicating that I put this green coating on the bottom of the zinc strip. So there has been a chemical reaction by me putting the strip of zinc into the solution of copper. And what I'm going to claim to you is that what has happened is actually an electrical process. What has happened when I've done this is we've actually got the rudiments of a battery. We have constructed this electrical power supply by sticking a piece of metallic zinc down into a bath of copper sulfate. Now, if we were to look closely at the equation, and before we go any further, let me point out to you that this is not chemistry class, and I am not going to ask you to regurgitate equations like this. But this is a symbolic representation of the chemical reaction that is taking place if you could look nanoscopically at the process. Again, do I expect you to be able to guess that this is what was going on in there? No. Do I even expect that you could write an equation of this type? No. But this is what we have as a symbolic representation of the occurrence. And let's try to digest what it's saying. See, this is a shorthand notation that chemists employ called a chemical reaction to explain the process. On the left, you see I have zinc with a subscript S, which means solid zinc. That represents the strip of zinc that I stuck into the beaker. Then I'm the other so-called reactant or thing that's combining with the zinc is the material that was dissolved in the liquid state in the beaker. And I've written it CuSO4 with a subscript AQ. Now to a chemist, what the subscript AQ means is dissolved in water. So the copper sulfate is in a solution, and the AQ is telling me that the state of the CuSO4 is that it's spread among a bunch of water molecules. Then I have an arrow, and the arrow typically in a chemical reaction indicates what becomes of the things on the left. And what becomes of the things on the left is that there's a chemical transformation. The materials change. The things on the right are not the things on the left. The things on the right are new substances. Now notice they are the same building blocks, but they are new substances. This is the hallmark of a chemical change. As a matter of fact, a long time ago, we talked about what Dalton said. Dalton said, in a chemical reaction, new materials are formed, but there is conservation of matter. Everything that went into the reaction comes out of the reaction. So what we're getting at is that no atoms of copper were lost, no atoms of zinc were lost, no atoms of sulfur or oxygen were lost. All atoms are accounted for, but they are rearranged and we have made new things. So that is what chemistry really boils down to. You take some things, you take them apart, you put them together in different ways, but you don't have any leftover pieces. When you put them back together, every piece that you took apart was put together to make the new material. Okay, so that is what has actually occurred. But now let's break this chemical reaction down a little further. And I will notice, and I will claim to you that both the copper sulfate and the zinc sulfate are what we called electrolytes. Now, I'm sure you've heard the term electrolyte before. This is very commonly, you can't get 2 minutes or you can't get 20 seconds into a Gatorade commercial without you hear them saying, it replenishes your electrolytes. Now, what does it mean to be an electrolyte? Well, if you digest what the words say, it means charge loving. And why it's charge loving is because they are charged species. They don't exist as neutral species. They literally exist individually as charged species in the solution. If you could nanoscopically look at the above equation I'm claiming, they're not connected Cu to SO4s. They're not connected ZNs to SO4s. Those things are individual charges. Now, the only reason they can get away with this is because of the theater that they're present in. Water facilitates them to be able to roam around in the beaker independent of one another. If you don't have the water present, this is not possible, and the zincs will stick to the sulfates and the coppers will stick to the sulfates. But water itself is kind of polar and has the ability to, its plus end yanks on the minus ends of the zinc sulfate, its minus ends yank on the plus ends of the zinc sulfate, and they literally pull it apart. One of the secrets in order for this to occur is that there's way more water molecules than there are zinc or sulfate molecules or copper molecules for that matter. So there's an inundation of water. The water attacks these electrolytes and rips them to shreds. So floating around in the solution, you actually have neutral zinc on the left, charged copper and sulfate on the left. Then on the right, you have neutral copper on the right, charged zinc and sulfate on the right. Now, before we move again, let me claim to you, would I expect you to know that this is what goes on? Would I expect you to be able to write equations like this? The answer is unequivocally no. I don't expect you to be able to do anything at all, anything like this. Just trying to represent to you the physical situation that is actually occurring. And that is, when there's an abundance of water present, the polarity of the individual water molecules is such that it has the ability to rip electrolytes to shreds. And in the solution, the electrolytes exist as individual charged species. Even to the most familiar electrolyte of all, this is true. And the most familiar electrolyte of all is sodium chloride. And I think if I mentioned that name to your mom and them would know sodium chloride is NaCl. When you put NaCl into water, and of course that is salt, when you put salt into water, it does not exist in NaCl units. NaCl is also an electrolyte. And as a matter of fact, what do you think that Gatorade is touting that it's going to replace? It's going to replace electrolytes. Most of what it's replacing is your NaCl. Now, it turns out there are other important electrolytes in you besides Na and Cl, but those are certainly among the most important. And it probably the third would be potassium. So that's resupplying you with potassium as well as sodium and chloride. Now, so what happens is when you sweat, of course, the liquid comes out of you, but dissolved in that liquid are the electrolytes Na plus and Cl minus, among other things. So when you drink a Gatorade, it's dumping more Na plus and Cl minus back into your body to help regulate the various functions of your body. Okay, so anyways, if I looked closely at what is really going on, I would note that this is how everything is actually existing in solution. Once again, the idea of Dalton is satisfied. Nothing is lost or nothing is gained. Now, some things have changed charge. Notice on the left, I have a change in charge in the zinc compared to what it was in the right. Notice on the left, I have a change in charge on the copper compared to what it is on the right. But otherwise, all the atoms are accounted for. No atoms are created or destroyed. As a matter of fact, if you look closely, no electrons are created or destroyed either, because the charge change that the zinc has undergone is exactly matched by the charge change that the copper has undergone. And as a matter of fact, if we think about that middle thing as a math equation, and the arrow as being like an equal sign, I have a sulfate or SO4 minus 2 on the left of the equal sign. I have a sulfate or an SO4 minus 2 on the right of the equal sign. And if this was algebra, your math skills would say cancel the things that are equal on both sides. So if I cancel the sulfate, I get an equation that shows how charge is transferred. Now, unfortunately, it's hiding behind my play button. And I don't want to hit the blue button because I'll stop the recording of the episode, or else, I'll stop the presenting of the slideshow. So I don't want to do that. But behind there, what it says is zinc neutral plus copper plus 2. After reaction becomes zinc plus 2 plus copper neutral. So the zinc is ultimately losing electrons, going from neutral zinc on the left to a cation of plus 2 on the right. Somehow zinc is shedding charge. Where does the charge go? Does it go into space? Does it get swept under the rug of the universe? No. The copper goes from plus 2 on the left to neutral copper on the right. So what we say is that charge is being transferred in this reaction. And this is very typical of many chemical reactions. Charge is moved from atom to atom. The atoms don't get destroyed or created. Really, the charge doesn't get destroyed or created. The charge is just moved around. So that is a spontaneous change. The zinc loses electrons, and chemists call that oxidation. Anything that is being oxidized is losing electrons, and the copper, we say in chemistry talk, is being reduced. It is gaining electrons. These things happen simultaneously. Now, what I'm representing in these two equations is zinc turns into zinc plus 2 by getting rid of 2e with a little minus. That means the zinc got rid of 2 electrons. On the bottom, I'm saying copper plus 2 gains 2e minus and becomes neutral copper. That's saying the copper is gaining electrons. These processes occur simultaneously. Zinc loses electrons, copper gains electrons. Now, what scientists have learned is that we can do this in a contained, concise, small device and use it to generate flow of charge. Remember, electricity is flow of charge. I'm seeing here that naturally copper will transfer, zinc will transfer electrons to copper. If I can put that into a little device, I can now harvest from that device flow of charge. And guess what I'm talking about? I am talking about a battery. Anytime you have a battery contains two terminals. The terminals of a battery are made from different metals. Traditionally, for decades, the batteries were all copper zinc, all of them. Especially in the good old days, you probably haven't even seen one of these. The good old silver ever-ready batteries. They were silver. They had like a cat on the front of them. And I don't know, they lasted like on Christmas Day when you were a kid, you got a new toy, it took 4D batteries, and you got up at 6 in the morning and played with your toy. By 9 o'clock in the morning, the batteries were dead, and your dad said, I ain't buying any more batteries, that was expensive. So you had your nice toy. Even I had battery-operated toys. I'm not that old. But once our batteries died, we didn't have a way to recharge them, believe me. So I had to wait till my birthday probably to get more batteries probably. But in any event, all the batteries were zinc and copper batteries. All of them. And they have, if you want, cut one open and look what's inside of it. You got a kind of like a gooey center. The gooey center has that dissolved charged material that we're now going to transfer electrons between. And if you connect them with a wire, you can harness and harvest the charge. So all batteries that we see are just doing little chemical reactions. As a matter of fact, Duracell still use this same setup. Now they've perfected it a little bit. Duracell, of course, is called the copper top battery. And the copper top battery has a zinc terminal. Copper is the top. That's the little bumpy point part. And then the can on the outside, the can part is zinc. So it's still using a zinc copper battery. Now, a lot of batteries these days are alkaline batteries. And I'm sure we've all heard alkaline. What does that mean? They like to use column 2 elements, in particular magnesium. Magnesium gives a little more punch. So an alkaline battery will use magnesium in place of copper. They still use zinc, but they replace the copper with magnesium. Now, guess what? Magnesium is a little more expensive than copper. So if you want to buy the alkaline battery, you better pay a little more money than if you buy your cheap old Rayovac can battery because of the materials that are being used to make the terminals of the battery. Okay, now it turns out that zinc giving electrons to copper is spontaneous. Now, what does that fancy word mean? Happens without any input of energy from you. Anything that happens spontaneous occurs naturally. So there's a natural tendency when you put copper around zinc that electrons flow from the zinc to the copper. So companies like Eveready and Duracell and Rayovac have learned how to harness this and make this into an industry. Turns out, of course, that is a very important industry. If you don't recognize the importance of batteries, I mean, even I carry 3 batteries probably with me at all times. You probably might even have more batteries than 3 with you at all times. So this rechargeable, now that they're rechargeable and renewable, that's a whole new bag of tricks. And we're going to, here on upcoming slides, talk about that as well. Okay, so what this led to was this individual named Luigi Galvani. And Galvani was an Italian scientist, as you see, lived in the late 1700s, he invented the battery. And it was called several things. As I say here, it's called the galvanic cell or the voltaic cell. Volta was another Italian scientist who worked on similar things. But the Volta and Galvani were the first people to really make the chemical storage battery, using a chemical reaction to make electrical energy. It's really kind of interesting if you look at what Galvani did. Galvani was actually a biologist. He wasn't really a chemist. And what Galvani was actually doing when he started investigating this was dissecting frogs. And when he dissected a frog, he had a fresh frog just killed or whatever, and he was messing around with it and cutting it with a scalpel. But the frog had only been dead for moments, really. And he put his metal scalpel down in the frog's gut somewhere and managed to touch one of his neurons, which is the electrical system of the frog. And when he touched the right spot where the nerves of the frog happened to be condensed, the frog legs started moving. And it was like freaky. So the frog was so freshly dead that the metal scalpel that he put in there was able to now flow electrons just like zinc does. It was flowing electrons into the fresh, still really not dead yet, neurons of the frog, and causing the reflex to contract the muscles and make the muscles of the frog move. So believe me, when he discovered this, he didn't understand anything about batteries, anything about electricity, really. He was really trained in life science. So he spent a long time investigating what was going on. He recognized it only happened when the frogs were really fresh. It only happened when the scalpel was really clean. It only happened when he touched a certain point. And then through all this investigation, very close investigation of what was going on, they eventually recognized that they were transferring electrical power into the leg of the conducting system of the frog itself, and they were generating a chemical flow of charge that became known as a battery. So Galvani made the original batteries back, as we can see, in the probably around 1780 or so. All right, that's going to be quitting time. We're going to continue talking about batteries and generating electrical energy as we move on. Remember, please, and I'm going to send out a reminder as well, make sure by Sunday evening you have completed Test 2, Activity 2. So until next time, peace out. You too.